Hi, my name is Gavin Cabral, and this is a video for Design Assignment 5 for Computational Multiphysics. This time around, we were given a quartz crystal microbalance that uses quartz and titanium as bridge layers. It's going to be fixed on each end, and we're depositing a shadow mask of gold thin films over the center through a length window. The sensitivity of this microbalance must be at least 0.0002% relative change in relative frequency per angstrom of coating. We're also given ranges as well as conditions on the bridge and shadow mask geometry that must be adhered to. Now, for the greatest response for this QCM, the thickness ratio of quartz to titanium should be the one that causes the most curvature for a given electric field in the quartz. Based on this, our goal is to determine how thick of a layer of shadow mask we can deposit under the outline sensitivity and geometrical constraints, as well as plot the sensitivity versus thickness for coatings of gold, molybdenum, chromium, and silicon dioxide glass. My personal involvement in this problem was creating and brainstorming the 2D and 3D flex models, 2D implementation in the design report, and the scripting and optimization portion of the design report. In modeling this problem, we're going to use the dynamic beam equation, which describes the behavior of a resonating beam. We're going to substitute harmonic solutions with the bridge boundary conditions, and then we can solve in Maple for the first plot of the resonant modes here, and then using flexural rigidity and material properties, we can then find the fundamental frequency for these test values. Implementing it to Flex was very similar to previous assignments, defining our variables, equations, our properties, piezoelectric and stiffness matrices for the materials, our strain definitions for displacement and mechanical strain alongside Hooke's law. Here our regions were defined in Flex. Here are all the matrices that were used. We oriented the quartz in the direction for maximum curvature with a given electric field. And for the ratio, we're going to use relations to Young's modulus to come up with this expression, and then enter the effective Young's modulus in the length direction used for the quartz and for titanium, and that gives us this ratio of 1.22 for quartz to titanium. Here we simulate the bridge, and the frequency we find is very similar to the analytical one found in Maple, so that validates that. Here we can see a simulation of this bridge. And then when we add the mask, that's without the mask, this is the effect it has on it, greatly increasing the fundamental frequency required. To implement our model into 2 dimensions, first we have to validate that it can be implemented in 2 dimensions. To do this, we plot our Z displacement in Z at a point in the beam that can be seen here, and we see that the change from -3 to -3.8 e to the -3 is so small that we can declare it negligible and thus independent of the Z direction. Then all we do is remove Z dependence in the flex code, and we come up with a simulation here of the first resonant mode of the bridge. To test our models, we're going to compare 2D to 3D by inputting different geometrical parameters within the constraints of the problem and comparing what we get. So first off, with a given set of values, we find 2D and 3D very consistent. Next step of values, 2D and 3D, very consistent. Third step of values, 2D and 3D, very consistent, where we can see the 2D is slightly greater as expected. This next set of values, very consistent with this trend of 2D being greater decreasing, but this is explained as due to the fact that now we're simulating dimensions that are longer in comparison to our first test case. And this is the final one. As we can see, they're consistent. And now moving on, we can look at graphs plotting the sensitivity versus thickness of the materials, and seeing a downward trend in sensitivity as we deposit more. And that's for gold. In terms of molybdenum, here we see the same thing, chromium the same thing, and silicon dioxide glass the same trend. So to optimize in Python, first we initialize our necessary libraries, provide the flex code as a string, have our empty lists here, and now we have our functions. So our find value function extracts a general value at a point of interest in the code we're trying to find. Relative change determines the relative change in frequency of a given simulation. Point validity determines if the current geometry being simulated is valid to the geometrical constraints of the problem. Get simulation values just extracts the frequency and quartz thickness and titanium thickness of a given flex simulation. Base frequency determines the fundamental frequency of a given flex simulation. Condition determines if the sensitivity condition of our problem is met by a given flex simulation. Interpolate is just a simple linear interpolation function that gives us an interpolated value for higher accuracy, and then we have our grid search here. So this begins by determining the step size of each parameter. Then we begin the loop for the bridge length. On top of that, we nest the loop for the bridge thickness, and then we also nest the loop for the mask length. And at this point, we check the validity of the geometry we're trying to run to see if it fits in within the constraints of the problem. If this is true, then a while loop begins that tests and iterates mask thicknesses over the current geometry. When sensitivity condition breaks, the function stops iterating thicknesses of mask and interpolates its final value as the value of thickness. And then we have our main function, which runs the starting bounds. The grid search used for sensitivity and thickness just generates a list of mask thicknesses and respective sensitivities up to the point that the sensitivity reaches 0.0002%. And then this function here just graphs and plots the results, which is repeated for each material. Our simulation tells us that once the sensitivity condition is met, the optimal geometry for the problem is a bridge length of 937 e to the negative 5 meters, bridge width of 234 e to the negative 5 meters, bridge thickness of 480 e to the negative 6 meters, quartz thickness of 264 e to the negative 6 meters, titanium thickness of 216 e to the negative 6 meters, window length of 268 e to the negative 5 meters, and thickness of gold mass we can deposit is 265 e to the negative 6 meters. Here you can see the errors, which are all from the final step sizes and account for the significant figures used in the problem.